Hi Zubin. Zubin, how are you? Okay, so let me start. Okay, so today I will be covering the topic of BDDs, binary decision diagrams, and yeah, for your assignment, so today's portion will be mostly the kind of the theory behind BDDs and what BDDs are and how you could construct them and manipulate them and how they're used to represent Boolean functions and so on. There is a specific open source BDD package called the CU BDD package. CU stands for Colorado University. So that is the one that you will be using in your assignment to implement in the CTL model checker. I've asked Zubin to install that and publish information and manuals and the API for the CUDD package. We'll be talking a little bit about that perhaps in the next class. We may not get to doing it today. So, but today's portion is just the theory behind BDDs. So you're all familiar with the normal forms for prepositional formulas. These are some of the standard normal form that are commonly used, CNF, DNF, and both of which are in negation normal form. But there is another kind of normal form which is built using the if-then-else operator. So I call it the ITE normal form, which with some restrictions can be made to become a canonical form for representing any Boolean function. And that's what BDD exploits to make the checking of satisfiability, validity, etc., very efficient. I mean, it's actually constant time, provided you can construct the BDD. So that is the biggest catch. So it trades the time space efficiency for time efficiency. So let's see what how it accomplishes this. So ITE normal form. So we first introduce the ITE operator. So denoted this way, it's a ternary operator with a test argument and two term argument, which can be any term. So it's an IT operator defined as this one. So if X is true, then it is takes the value of Y naught. If X is false, then it takes whatever is the value of Y1. Fairly familiar operator that you see in programming languages. Is just an implication. So an INF Boolean form is defined as follows. INF is a Boolean expression built entirely from the IT operator and constants 1 and 0, with the restriction that the test, what appears as test, the test must be performed only on variables, that is positive variables. So these tests, what appears in the place of test has to be a variable in a positive form. Y0 and Y1 itself can be any arbitrary ITE. So it's a nested ITE operators. That's what forms the ITE normal form, the expression. So it's not that hard to see any Boolean expression can be expressed in this form. I mean, you can do that by, you know that or, and not form a universal operator. You can easily express those three things. But there is another characterization that I'd like to present for proving that this normal form can express any Boolean expression. So let t, where t is a term, t within brackets x be replacing x. They denote the result of replacing the variable x inside the term t by these Boolean constants, either 0 or 1. Then t is the term t, the Boolean expression t, is easy to see that it's equivalent to, if x is true, then it is t with whatever the value of t is, with x with 1, substituting 1 for x. Or if x is 0, then it is the truth value of t is replacing x by 0. This particular thing is if you apply it as a rule, it's called Shannon expansion. So any Boolean expression having any operator, any Boolean operator for that matter, can be converted into an INF by repeated application of this rule, the Shannon expansion rule, to each variable that occurs inside T in some order. Okay? And you keep repeating this until you get an ITE expression for T, an arbitrary Boolean expression. So for example, consider this Boolean expression denoting a Boolean function which has over variables x1, y1, x2, and y2. The Shannon expansion producing INF for T can be represented as a decision tree. See, on the right side, I've shown you the actual Shannon expansion with each sub-term given a unique name. The way you do is you start with this expression. Here, I've chosen this particular order of the variables to expand using Shannon rule. So each node here can be considered as an ITE operator. Okay, so the dotted line gives you the case, the sub-expression for the case when x1 is 0, and the solid line gives you the sub-tree appearing on the right side as a child of the solid line. Gives the expression which you obtain as a result of substituting 1 for x1, and so on. Okay, so that's what is happening. So T1, T0 are the term rooted at y1 on the left and right, and so on. Okay, so this is an IT normal form can be viewed as a decision tree. Okay? And so it's called a Boolean decision tree. And you can see that any Boolean expression, a Boolean function, can be represented in this fashion. So, in other words, when you do this, the leaves are actually the evaluation of the function for a particular assignment to the variables, particular truth assignment to the variables that is given by following the edges from the root to that leaf. This is all this is all clear, correct? This is all fairly easy, so I hope it's all clear. So this is a starting point for the definition of eventual definition of what we introduce as BDDs, Boolean decision diagrams. So obviously this INF form, right, it's a normal form, it's still not a unique normal form for a Boolean expression, because depending upon the order in which you choose to make the decision on, you can get different ITE expressions for the same Boolean function. So since, as I said, we are aiming towards getting a canonical, that's a unique representation for Boolean functions, one way of making it is to fix a particular variable ordering. So for a given variable ordering, the INF is unique for that ordering, because you can use the Shannon expansion rule to actually decide on the variables in that order. Okay, so the two important things to notice is the test in each of the IT operator. What appears in the test is a simple variable. Okay, so the other expressions in the left and the right side, they can be arbitrary ITE expressions until you hit 0 and 1. Okay, so that's decision tree. And for given variable ordering, that is indeed a unique representation for any Boolean function. So is that clear? Any questions? Okay. I'll start my video so you can see my face. Yeah, so this is quite good, but obviously you can see that this representation is not very compact. Okay, it's exponential in the size of the variables. So you want to go from a decision tree to a DAG. So that's when you get a decision Boolean decision diagram. Okay. So there are three reduction rules that we use to go from a decision tree, ordered decision tree. So that's an ordered decision tree because we are choosing a particular variable order, to an ordered binary decision diagram. So the first two rules, they're actually you try to share as much of the subtrees that are identical. Okay, I mean they actually share all the subtrees that are identical in the decision tree. So all isomorphic, that is equivalent, identical subtrees must be shared, including the leaves. And of course, the second one is all variables occur in the same designated order on every path from root to each of the leaves. Okay. So reduction rule 1. So you merge all the the ones and zeros at the leaf, the nodes that contain ones and zeros, okay, into just a single copy for 1 and a single copy for 0, and then correspondingly merging the edges, okay, that go from other nodes to 1 and 0. So that is reduction rule 1 for merging the leaf nodes. Second reduction rule is applicable for non-terminal nodes. Okay, so if you have the two terms root, yeah. So if A rooted at a particular node, say A, identified as A, if they have yes the same subtree then you kind of merge them. Yeah. So here is the example, I mean, to see. So as a result of applying rule, yeah, rule 1 is fairly clear. So you can see that the subterm rooted at x2, at x2 on the left side, and the subterm x2 are identical. Okay, and so they have the left, they have the same variable in each node, and the left and the right children are the same all the way to the leaves. Okay, so y1 and I mean the subtree is rooted at y1, and these two here are not identical. Why? Because you can see that the solid edge in the the one on the left side goes to 0. It goes to 0, whereas here it is the dotted dotted. So they are not. They're obviously not identical. So here you can merge all the ones, and you can merge x2, the two terms rooted at x2. So what you do is, since they're equivalent, then you take the edges going out of y1 redirected. You only keep one copy of each of those subterms, and then you direct the edges of its parent appropriately. So from here, you go to a DAG representation of that. So y1, the solid edge, the high edge was going to 0, so that is there as is. So, and the dashed edge goes to the single copy of x2. Yeah, and you do this kind of bottom up when you do it. I mean, you can do it in another order, but as long as you eliminate all repeated shares, and you get all the sharing that's possible, and that's what you're supposed to do by this rule 1 and rule 2. And you can see the compactness that you can get. I mean, at each level, if the subtree, if the levels are, there are lots of levels, and then anytime you get some sharing at any particular level, there is kind of exponential, sometimes exponential amount of compactness that you can actually end up getting by using these two rules. So in this case, we're using the variable ordering x1 less than y1 less than x2 less than y2. So that, as a result of this merging, that is also preserved, okay? Obviously, because you are directing the edges in the same way. So as you can see, on every path that goes from the root to the leaf, the variables appear in the same order as the variable ordering, chosen variable ordering. So for example, this is on the one on the right side is an order violating thing. I mean, assuming that the ordering that I intend to use is x less than y less than z, then this one is not, because on the left side, it so the order is preserved, but the path on the right extreme does not preserve the thing. Does not preserve the order. See, as you can notice that you don't have to have all the variables occurring on every path from the root to a leaf. Yeah. So it depends on whether the value of the Boolean function, what the value of the Boolean function is for that particular assignments. In this case, if x is equal to 0 and y is equal to 1, the value of z does not impact the Boolean, the value of the overall function that the BDD is representing. that is quite possible. There's one other rule that will take you from ordered BDDs to what is considered as, a fully ordered, fully reduced BDD, and what people generally refer to as BDD is actually reduced ordered Boolean decision diagrams. Okay, and to motivate that reduction, I want you to observe these examples. See, this is a single node, representing the constant 1 on the left. Both B and C, they represent they all represent 1, as a matter of fact. Okay, so x1, so if x1 is 0, it goes to 1, x1, 1, okay? As a result of doing the, applying the previous two rules, sometimes you can end up having these kinds of redundant nodes. So when you have both the low edge and the high edge going to the same subtree, then what it means is that node x1 is redundant, because the value for that, regardless of what you assign for x1, the Boolean function evaluates the same thing. So you can actually get rid of, that such nodes, okay, whose low and high subtrees are identical. They go to the same node. Okay. So the third rule is exactly eliminating the redundant rules. So then, when you eliminate that, you just take all the incoming edge to its unique child. Okay, and that's what you do to get rid of that. So in this case, if you got rid of that, all of this will collapse to 1 in this case, and here x1 will just go to x3 directly. So these are the 3 rules that you have to repeatedly apply to the binary decision diagram to get the reduced version of that after choosing a given variable ordering. So henceforth, I'll just use BDD, and I will assume that all our BDDs are ordered and reduced. So any questions so far? Things are clear? Okay. So here's a formal definition of a binary decision diagram. That is ROBDD. So here it's both versions formalized. So binary decision diagram is a rooted, directed acyclic graph with 1 or 2 terminal nodes with outage. That is, terminal nodes with outage labeled 0 or 1. Okay. So I say 1 or 2 because sometimes if the whole thing, there may not be any paths leading from the root to 1 or 0. So the only leaf node can be 0 or 1. That happens. Yeah. So you would probably guessed when can that happen. If there's only a 0 node, then it is that Boolean function always maps all its different combinations of inputs to 0, and so the leaf would have only 1 if all combinations are mapped to happen to be mapped to 1. Then a set of variable nodes, u without degree 2, The two outgoing edges are given by the two functions, low u and high u. Okay. So here I've just marked, given a label, a unique ID for each of the nodes. Okay, with the ID 0 being given to the constant node 0 and 1 given to the constant node 1. Okay, so each node will have a variable associated with it, okay, which is, we'll assume that it is given by the function var of u. So a BDD is ordered if on all paths through the graph, the variables respect the chosen linear ordering on the variables. And an OBDD is reduced if, as I said, no two distinct nodes U and V can have the same variable associated with it and whose low and high successor different. It cannot have no two distinct nodes can have that. That is, in other words, if variable of any variable U and variable V are the same, low and V high are the same, that implies that there is a unique node in the graph representing that. Okay. So if there are two nodes with the same variable associated with them, then what it means is that it's low or high or both has to be different in the RO BDD, the reduced BDD. Okay, so that's the formal definition. So since we saw the association of between BDD and the IT expression, so every node in the BDD has a Boolean function that is associated with it. Okay, and the Boolean function is actually defined by the ITE term that you get out of replacing each node by the ITE. Okay, so by the ITE form. Okay, that's the function that it is done. So the canonicity theorem can be stated then as follows: for any function f, Boolean function, n variable and a variable Boolean function, there is exactly one ROBDDU with for a given variable ordering, okay? And that's the main theorem. Okay, I will not prove the theorem here. I mean, it can be shown by induction on the size of the on the number of variables used in the function. Okay, and then you can show this by using the 2-3 reduction rules. So that's the important thing, that every Boolean function for a given variable ordering has a unique representation as a ROBDD, as a BDD. Okay. What we'll be doing here is looking at how these these BDDs can be manipulated, and what can be how they can be constructed and manipulated, so that and then we can perform various operations on them, usual Boolean operations, including existential elimination operations, which are the things that we need while implementing model checking algorithms symbolically. Yeah, some summary of observations about what we've seen BDD. So variables always and variables on the path leading from every path leading from root to the leaf is always in the variable ordering. I mean, chosen order, the variable order. So every path from root to a terminal node, one gives a sat assignment. Okay, and every path from the root to a leaf to zero leaf will give an unsatisfying assignment of the Boolean function denoted by the BDD. Every node in the BDD, as I mentioned, represents a Boolean function. So the one at the root represents the entire, the entire function denoted by the function denoted by the entire BDD. But the functions at other nodes, they represent a restriction of the function at that root. For example, the function rooted at node 5, labeled as 5, is a restriction of whatever the function denoted by the node 7, with x1 being restricted to 0. Similarly, the Boolean function represented by node 6 is the function corresponding to node 7 for when you restrict x1 to 1. Okay. And that itself can be considered as another function that is over the remaining variables. So every valid formula, when you even by the way that you construct the BDD, will end up being identical to 1. Okay. So in every unsatisfiable formula will be uniquely represented by 0. Therefore, once you construct the BDD, checking satisfiability or unsatisfiability can be done in constant time, just by, if you end up getting 1, it is thing. And once you construct the BDD, getting satisfying assignments can also be done in linear time by just traversing the path. Okay. So what's the catch? Satisfiability was supposed to be NP complete. Any answer? An obvious answer.
The number of nodes in BDD can be exponential.
Yes, the size of the BDD can be exponential. Okay, that is, for certain, yes. Okay, and that's the thing. I mean, I think I have a slide, maybe not this, and I can show. So the size of the BDD is very much impacted by, with the same function, it can be impacted severely by the variable ordering that you choose. Okay. So the size is very sensitive to the variable ordering. So for the same Boolean function, depending upon the order that you use, you can get a very compact one or a very big BDD. And there are some functions that have been shown to have even the lower bound on the size can be exponential in the size of the number of variables in the BDD. So that's even the lower bound can be exponential. So those functions, those kinds of functions, those classes of functions are sometimes called multiplicative function. For example, I mean, simple addition and additive or addition-like circuits are always have linear representation, whereas multiplication bitwise multiplication. That's an example of a function that never, I mean, has minimum exponential, you need exponential size. Okay, so that's the catch. Okay, but you know, depending upon yeah, so if the kinds of functions that you end up encountering, for example, during your doing model checking search and proof search, etc., happen to be compact, then this can be a winning way of doing things. So here is an example. So this is a function which, you know, just does what is shown here. It just checks if is one of them are thing. And so if you choose the ordering A1 less than B1, A2 less than B2, A3 less than B3, you'll get a very compact BDD. But if you intermingle these things, then it explodes. Okay. I mean, there is some, you know, generally BDD packages use various kinds of heuristics, and it can also, yeah, yeah. So, I mean, there is a kind of intuition that you can get. See, this one, the value of this function. See, is if, for example, if your Boolean function, the evaluation of that is such that it's the truth value at the output is independent of the order in which of the order of values, ones and values taken by these variables, then you actually have constant size can be done. I mean, so here, I mean, referring to this, see, if you do A1, B1 in this order, because just choosing by looking at A1, B1, you immediately get, for certain valuations of A1 and B1, you immediately get an output. I mean, you get an output independent of the other variables. And that's why, you know, you get a compacting in here. Whereas if you mix the order, then for each valuation of A1, until you know, choose a in the ordering evaluation for B1, you will have to carry along all possible combinations of in the ordering of the valuations for the other variables, and that's what ends up complicating, making the size of the BDD large. Okay, so you know, there is it depends on what, you know, how there is a dependence between the inputs, the output to the inputs, okay, and what are inputs for what things. If there is some analysis of that thing is, okay, you can do a priori, then you can choose the variable ordering. But unfortunately, doing this, choosing the best ordering itself is a hard problem, an intractable problem. Obviously, because if you are able to solve that, you know, you'll be able to crack the Boolean satisfiability problem. And since that is NP complete, this problem is also cannot be solved algorithmically in polynomial time or less, and in an efficient way, and therefore you will have to use some kind of heuristics doing it. Okay, so that is the thing. So choice of the ordering. So what C packages like CUDD and even modern BDD packages, they do is they do some you know, high-level analysis of the Boolean structures, of the structure of the Boolean functions at a certain level, and then use certain heuristics. But the other important thing that they do is, and we will see how, I mean, that we will see. So the next part, you know, I'll discuss how to construct BDD for an arbitrary Boolean functions. What kind of you know, operations, you know, if you want to construct various things, Boolean connectives, and you want to put them together. So sometimes what the packages they Boolean practice they do is they try, as they manipulate the thing, if they try to change the ordering on the fly to get the thing. If as a result of doing a particular operation in your BDD, you think that the size is exploding, then on the fly you can change the variable ordering to get it. So there is some technique called dynamic variable ordering technique. We will not get into those advanced things, but there's one important thing that you will have to see, and how exactly these BDDs are constructed. So see, how do you construct BDD? I mean, given two formulas, phi1 and phi2, okay? Normally what you have two formulas, and you are building a bigger formula using some connective, Boolean connective arm, okay? So, when you're constructing CNF or some other form, even for a SAT solver, this is not even an issue, because all you do is just put the two things together, and then you construct a bigger term. Whereas here you are, you have to do some manipulation in order to get that. So it would be good to have, and I mean, because there you don't care about any of the variable ordering and so on. So even if you already have two BDDs, the BDD for phi1 and phi2, with a particular given ordering, the challenge is to compose the two BDDs in such a way that you preserve the ordering and the reducedness conditions. So therein lies the challenge. Okay. So that's why it is not completely obvious. Of course, you could construct afresh from bottom up every time using Shannon expansion. Okay, and as you construct that, every time you can construct it bottom up, but that's not practical. You really want a procedure where given that, assuming you've already constructed BDDs for the arguments, you want to find a way of merging, so to speak, the two things in such a way that you can construct a order preserving ROBDD for the same ordering for phi1 up, phi2. And these techniques, these algorithms that do this, they all walk through the BDD for each of the arguments, phi1 and phi2, and do it. And the somewhat surprising thing is that these operations can all be for all connectives, including existential quantification over a formula will also be, will be implemented as one of the operations over thing. They can all be done, in some cases linear in the size, linear in the summation of the size of the two BDDs, okay? Now, I mean, unless the function represented by the BDD itself has no compact representation, then you are in trouble. So we'll show you a way of merging the two BDDs. Then all these require certain kind of data structures, so that walking through the BDDs can be done in efficient way. So these are some of the things that I will take you through in the rest of the lecture. Although in your assignment and so on, you'll be using all these operations come as built-in operations over the package that you'll be using, and you'll be using them as black boxes. But how they construct would still be instructive for you to learn and have an idea of. Okay, so first what I'll do is I'll kind of show you how it is done by taking some small examples and then give you the general algorithm. Suppose you want to do x plus x prime. Plus is or, prime is not. Okay. So I want to apply the plus operation on the BDD representation of x. First, I've taken some base cases, and then I'll get to the simple cases, and then I get to the general case. So what is the representation of x? So here is what you do. I hope you can see this. Yeah. So x, the variable x is represented by the BDD given on the left here. So what you're trying to do is, and the BDD on the right, it looks exactly the same except that the 0 and 1 are flipped. Okay. So the negation of x, all it has is flipping of the two. So I'm trying to construct a BDD, which is the result of applying the plus connector to these BDDs. So the algorithm first checks if the looks at the variable at the root. Here, in this case, the variables are the same. So it depends on whether your the two variables at the root are at any given node. This is a recursive. You recurse down the BDD to do this application of plus. And what you do, it depends on whether the variables at these nodes that you're trying to merge by doing this operation, if they are equal, less than, or greater than in the variable ordering. So in this is a case where they are the same. So in that case, what you do is you just keep the node with the same variable, but you apply plus on the left subtree of. You apply plus on the low and the low subtrees of the two BDDs and the left. Okay. So in other words, in this case, you you construct a new BDD with the same variable at the root, and then you do plus on 1 and 0, and plus on 0 and 1. So at the leaf level, you directly apply. So in this case, 1 plus 0 is 1, 0 plus 1 is also 1, and you end up getting this one. Okay. And after that, you have to do the reduction. Okay, so end up, in this case, you eliminate redundancy. And so there's a merge, and then as you merge, you will have to, you merge by preserving the ordering, and then you have to apply either as post, or as you do the merging, you can ensure that it is reduced by applying the reduction rule. So in this case, because you end up creating a redundant thing, so it will reduce to 1, okay? Which is what you would expect. X plus x prime is 1, okay? So that's roughly how. So there's the other case, for example, when you do this, x plus 0, yeah, by the way, 0 is, has no variable. So we assume that, that the constants in the variable ordering, they are, the highest, okay? So that's the assumption, okay? So because they appear at the bottom, therefore, although they don't have any variables, we will consider that they are they are in the highest in the ordering. So in this case, x is less than 0. So when you have the two, and you can extend this to if they're even variables. So when you do that, then what you take is you take the one that is greater. So you will and then you do the plus on the entire right-hand BDD to the low end of x and high end. So what you do is you take the entire thing and then do x. Here it is 0, so you do 1 plus 0 and 0 plus 0 plus 0. So you get x10, which is the same as what you had, and that's why this is marked as just 1. Okay, so in the case with the two variables, so there's another more complicated case. So here it is indeed a variable. So for example, here, if the variable ordering, I'm assuming x is less than y in the third picture. So then what I have to do is I have to take this entire BDD rooted at 3 and then do a plus of it with the left, the low subtree of x, and the same thing with the right subtree. Okay, so that's what the and that's how we recurse now. Okay, I mean, if y was less than x in the variable ordering, you'd have done the other things. You'd have taken 1 and then taken that down the right side BDD to do it. So here, following this, so then you will have to recursively apply the plus operation on the left side. So you do 1 plus 3. When I say 3, I mean over this whole thing. So that you will further recurse down and you will get this thing. And in doing the plus operation on the node 3 with the constant 1, you will have to repeatedly apply again as you did, and you finally end up getting this thing. So see what is going on here is the basis for doing these, recursing it this way down is actually because of the if then else semantics associated. You remember that each node here you are applying an if then else operator. So what you're doing is, where I'm explaining as though I'm doing it on BDD, but you might as well consider as doing this operation on the corresponding ITE expression associated with that BDD. Okay, so if that is, say, so this, if you have an ITE expression, x implies T1 or T1, T2, and x implies S1, S2, and if you're trying to do an operation on that, these are all equivalence preserving. You can now, if they are XX here, then you can take it down, and you can see that these two are equivalent. You can push up completely down on both sides, okay? Or, you can push the entire one side down the other side, okay? This is like, the distributive version of that. The operation distributes over ITE, and you can check the equivalence of all these laws. And that's why doing these operations are all equivalence preserving on BDDs. And the way we do it, we will use the variable ordering to decide how to do. So, so that when I do this, I will do it in such a way that I will preserve the ordering. So that is the thing. So is that clear? So I'm trying to, I'm actually establishing the correctness of doing this. When I explained it as manipulation over BDDs, it seemed like, why should it, obviously the question will come, why is it, even sound to it, to do it? And these laws is what I explained. So you do this on the right side, you apply that law when you see the variable at the root not being equal, but rather one is less than, greater than in this case, or less than. Okay, so depending on that, you try to keep one side the same, then you push the other one down the other side. Okay. So, and see, and this is how, I mean, I've explained this algorithm is parameterized with respect to any operation that you do. So, because eventually you will be doing the operation only at the leaf level. Okay, so you know, so this kind of recursive way of merging depending upon the variable ordering is applicable to any binary operations, binary connective of you know, Boolean binary connective. So any questions here? So these are some small examples. Now I'll be introducing the general procedure. Do you have any questions here? Okay. Oh, this is another example, slightly bigger example. So I'll first introduce the procedure and I'll leave this as an exercise for you to hand simulate it. Here is the general procedure. By the way, this particular topic is not included in the model checking book, okay? But there is I'm using a note, a particularly good notes on BDD, which I will upload. And there's also a chapter in the decision procedure, the book on decision procedures for propositional logic. It's a book on SMT decision procedures, which has a chapter on decision procedure for propositional logic. And I think that has a discussion by one of the authors is the same, which I'm using as a text book, as a reference text book for the SMT course. That has a chapter. That chapter also uses this notes from which I'm directly constructed the material for this lecture. In any case, I'll upload that, and that has these things, and I've used a lot of material from that notes. So here is the general procedure. So here, so given two BDDs rooted at nodes whose IDs, unique ID are U1 and U2, it describes recursively how to do the construct the result of applying a particular an operator. Here it is denoted as star on U1 and U2. So the base case is when U1 and U2 belong to is either both of them are either 0 or 1. So then you do it directly, okay? Otherwise, there are three cases to consider. If, as you recurse down the two nodes that the two BDDs, the variable at the root of the two BDDs on which you're trying to apply the binary operation, if the variable strengths are equal or one is less than the other, and the second one is less than the first. Okay, those are the three cases. So if both are equal, then what you do is you apply the operation on the two corresponding low children and the high children, and you make a new node, because as the result of doing this, the BDD that you end up creating can be representing some of the function. Therefore, I'm here using a make function, which is which I will introduce later on, which constructs, which adds new nodes representing new BDD to your data structure. Okay. So, but what you have to note down here is that you recurse on both sides by just taking the two lows and the two highs, and then you apply them. Whereas if the the first variable u1 is less than variable u2, then you keep the right BDD intact, and you traverse down the left subtree. I mean, on the left BDD, by taking the you keep u1 at the same, because u1 is less than u2. So you have to the BDD that you have to create has to keep u1 at the same place, and u2 has to be inserted down the BDD in order to preserve the variable ordering, and that's why it keeps where u1 and then applies the OR on. It applies the Boolean connective by keeping the whole of u2 and on the low subtree of u1 and high subtree of u1. Yeah, if the comparison is the other way, then you will recurse down the right subtree, keeping the BDD, the left BDD, the same. So as you can see, this one you can actually do in one pass by recursing both the BDD structures. Okay, any questions? So this pretty much takes care of all and or any Boolean binary connectives. That's how you do, and you see it is fairly efficient. In the size of the BDD that you have. Okay. Any questions here up to now? Okay. So here I will give you a bit of a glimpse on how you could what are some suitable data structure for representing this. See, you can do this merging operations first and then do all the reduction later on, okay, as a second step implementing. But the way that it's being done here is, it's also more interesting that this, while you do this merging, while you walk down the BDDs, the way the making of new nodes is done automatically preserves the all the reducedness properties. Okay, and that is, so this way of recursing down preserves the variable ordering, but you still have to make sure that all the redundancies are eliminated, and you preserve this property that every node created, the function corresponding to every node is unique in the BDD, and that you will see once I introduce these data structures. How make is implemented will make it clear as to how that is preserved. So, for example, there are each BDD, the graph is represented by two tables. One is a node table, which, given a variable I, which is a function, so node table T, which is constructed using this U. So it what it does is, given a variable I and a BDD to be used as its low subtree, and another BDD, so each, when I say BDD, it is represented by a unique ID at that of that node that is rooted at that. So it takes a variable and two node IDs. Okay. So by the way, in this, yeah. So as it does, so like I said, the variables. So here there are two IDs that I'm using. So don't get confused with anything. So there is a unique ID for each of the nodes. Okay. And there is also variables, okay? So in the table that I've shown here, so the variables are ordered by assigning 0 for one. I mean, sorry. I mean, the variable is yeah. So you will start with, I'm assigning the variable number as per the ordering. Okay. So here the ordering is x1 less than x2 less than x3 less than x4. So I've numbered them 1, 2, 3. Yeah, the variables are numbered as 1, 2, 3, 4. And as I noted early on, I will give the max number, variable number for the constants, okay? Because I have to push them in the thing way down, okay? So, and the unique ID is constructed on the fly, okay? That is given by as you construct new BDDs, result of constructing new BDD is adding a new entry into this node table. So what does that, and that adding the, when you add the one, it creates a new ID, unless, the result of creating that BDD is already there. Okay, that check is not as part of it. So, for example, here, this one is represented. You can follow this chain. Okay, so the unique ID given for the constant nodes are 0 and 1. Okay, and at 2 is the unique ID given for the one that is rooted at x4 on the left side. Okay, so it's, and so that has variable 4. So the node 2 variable is 4, and its low subtree is the constant. Okay, constant 1, because the dotted edge is 1, right? So it's 1. And the solid edge, that's the high subtree, that is constant 0. Similarly, 3 is the flip of that. Okay, it has the same variable, 4, but the low and high subtree are the reverse, and so on. So x3, for example, has its variable 3 in it. That's the associated variable, and its left low subtree is rooted at the node with the unique ID 2, and the high with the unique ID 3, and so on. Okay, so that's how this thing is created. So in order to check if something is already a BDD that you want to create is already there, and to make that operation efficient, you also keep the inverse of this, maintain the inverse of this table, which is a lookup table, which can be implemented efficiently using hash functions, and that's how most BDD packages implement it as. Okay? And that table has, the way it's constructed is using a function h, because we usually use hashing for that. So given an I, a variable, a triple, a variable, and a unique ID of a BDD rooted at L and H, it uses the hashing function, to see what the unique ID, if any, of that BDD, if it is there, in the node table. In that sense, it is the inverse. So for example, here, so this is kind of maintained as you construct the BDD on the fly. So in this case, for each of the triples, it gives you. So for example, 156 is mapped to 7 because, yes. So 5 is, yes, the Yes. So the variable 1, I mean, the node that has variable 1 whose low subtree is rooted at 5 and 6 is this one. Okay, rooted at 7, and that's what you, and it maps to 7. And 240 is mapped to 5 because 5's low subtree is rooted at 4, unique ID 4, node 4, and this one is 0, and so on. Okay, so as you construct new nodes, now here I'm showing after a posteriori after the construction, but as you construct the BDD, that you will build these tables as well. So each table has 3 operations: the initialization and the add operation is the one that, given a triple ILH, if it is, it adds a U. Okay, it constructs a new entry, creates a new ID to it, and then bar of U and low of U and high of U just give the variable, the ID of the low subtree and the ID of the unique ID of the high subtree associated with each of those things. Now, the operations on the lookup table are very important, okay? There's a member function which checks if ILH is in H, okay? If it is already there, then what means is if it maps to a valid unique ID, that means that it is there in the node table, that you don't need to create another copy, okay? If not, then if it is there, then it looks up for it and finds the that unique ID associated with that. If not, then you can safely insert that thing to build up the lookup table in the lookup table. So that's how these things are maintained through hash functions. These things can be done in almost constant time. Okay, so I hope you have got some idea of the data structures. So here is how make is implemented. So make takes T and H. It's parameterized with respect to that given a T and an H. So what it does is it takes a new triple. Okay, it's trying to construct a you use it to construct a new BDD with variable associated with the node and any given low and high. See, that's what you needed, when you were doing the manipulation for applying the operations that you needed. So here it does by preserving all the reduction rules. So the first line checks for redundancy. If L and H are identical ID, then it just returns one of them. So that the redundancy check, okay, both it prevents from the same node, both L and H being if they're going to the same node, then you're not supposed to insert it. So if L is equal to H, then it returns L. It means that it does not add anything. As if it is a member, if it is already there, then all it does is, if it is already there, which you can check using the lookup table, then it just looks up in the table, in the lookup table, its unique ID, and then just gives that. Okay? Otherwise, you create a new node and you insert it into both T and H, and then you return that. So that's what is interesting here. So it just kind of merges into make, and that's what is used in the apply. Okay, that we saw every time that you had to make a new a BDD as a result of applying the function as you recurse down the diagram, you use make. Okay, so here. So when you tear a BDD apart and then you apply and then you reconstruct it, that's when you do make. Okay, because when you do that, you either create a BDD that is already there in your repository, or it is, or you have to make a new node. So I have an example here. Now this example, see, what I illustrated with you previously was generally working on BDDs as directed graphs. Here, now I'm showing you a specific implementation of how all these things are preserved. Okay, so while this is a bit of a detail, I still thought this would be is interesting enough for you to get a grasp of and what happens inside the BDD. So here is an illustration of the thing. So here there are two. Suppose I want to apply OR, the OR operation on these two Boolean functions represented by these two BDDs. So this represents x1 if and only if x2. This is a simple not of x2. So that's why you see, so this is the variable ordering. So what is stored inside the thing are the unique IDs of the nodes. The variable numbers are 1, 2, and of course 3 for the other one. So these two are BDDs over two variables, x1 and x2. So what is the result of getting, what is the result of doing this? First, before you see how it works, so and I'm going to simulate this, even if I don't have time, so I'll only take maybe 5 more minutes. If not, have all the slides, go through that. It's just simulating the apply node. So, but I want to see what the output ought to be. See, here, notice one thing. The right side, not of x2, you're convinced that not of x2 is represented by this BDD, okay? And you notice that is also part of this, because in constructing the BDD for x1, if and only if x2, not of x2 is being used. And that's why you see this BDD also appearing inside here, okay? Although I'm showing it separately here, when you construct the BDD, there's one big repository of BDDs for all the functions that you might have constructed, okay? To begin with, you construct, when you use CUDD package, you will realize that what you do is you have to first determine, allocates a certain number of variables for your application, okay? And then you construct all the nodes corresponding to variables, okay? And that it does automatically. So, and then in the way that you construct, you'll only construct one unique ID for every function that you will be needing along the way in constructing your BDD for the, the function that you so desire, that you desire to construct for. Okay, so what happens is, that's why, so the unique ID for this argument is the same as here, because that is already part of this argument. That is that is by the way that you construct is it happens. So yeah, the result of constructing, I'll first show you the result. So what I'm doing is, so this is the original BDD. I've repeated it here. And you're doing an OR of this entire BDD with this BDD as the second argument rooted at 4. Now, if you did the this app applying the procedure, this is what you will end up getting. Okay? And you'll notice that some of the existing functions are no longer used as a result of doing it. So for example, the functions rooted at 3 and 5 are no longer needed to represent in the BDD for the result. Okay? You can convince yourself this is indeed the result. Okay? You know, so but what I want to draw your attention to is that it throws a, I mean, 5 and 3 are no longer needed, but it creates a new node for the you know, resulting BDD that you you know, that you get. So these 3 and 5 are no longer used. Now either you can choose to keep them or you can choose to throw away. Okay, so that is up to you. You know, to do so, but certainly the result BDD that you get has no reference to the BDDs rooted at 5 and 3, because that is not needed to represent that function in the BDD fashion. So that can happen. So that's why I've shown that in blue. Okay, so what I will do is, I think I will, I mean, there's no point in my, I mean, I'll be just, it's getting towards the end of the lecture, and you know, it'll probably, I will, you know, your attention span might not be as wonderful as in the beginning. Therefore, I will let you, all this is doing is simulating the app, the apply recursive function on these two BDDs as it is represented into, you know, in the data structure there, and but in terms of make, okay? And I will have you go through it yourself, okay? And I'll stop here, okay? And take any questions you have. Next time, I will, at the beginning, I will introduce you to CUDDD package briefly, and yeah, CUDDD package uses a slightly different version of BDD, which is even more compact than this this version of BDD. It uses what is called, yeah, a different kind. So you need to, I need to introduce you to that, and I mean, it really, yeah, does the same kind of applications. So that's what I'll do next time. Okay. So any questions? I'll stop here before I. Okay. So by the way, Zubin, were you able to download CUDDD package? Zubin,
yeah, it's in the repositories for my Linux distribution.
It is on the repository, means Moodle, you mean?
No, for my Linux distribution. So I was able to install it quite easily.
You were able to install it and do it. So maybe we should, yeah, before next time, we should just sync up and then see what it is that you, if you want to do something similar to what you did. The thing,
Okay.
I'll try. Today is already Thursday, so it'll be next week, you know, by the time. Okay, so,
Okay.
yeah. So it's already loaded in Moodle, and you know, maybe you guys, if you have time, you can play around, download it, install it, and then look through the manuals and so on, get acquainted. Yeah.
Can I just ask, what's the package name?
What is the package?
Yeah, for CUBDD.
The name of the package. It exactly this you know, BDD things. It gives you a list of functions.
Yeah, so is it just CUBDD? Because I was searching with that in the repositories and didn't get anything.
In which repository?
So I
Oh, I'm
believe I'm
sorry.
running
It
this.
is not yet uploaded on Moodle. I'm sorry. It's
No,
not.
no, I'm not. I believe I'm running the same repository as Zubin. So I did a quick search right now. I couldn't find it. So I was thinking, is it some uh, other name than CUBDD on
It's
the
called
Arch Linux?
CUDD.
CUDD. Okay, I see.
No, CUDD. Double D.
Okay, okay.
CUD
CU
package.
CU double D. Okay, okay. I think I said.
CU double D package. Yes. So what it provides is this. I think that one of the reasons it's a little bit, not one of the reasons. Okay. It uses a slightly different one. I mean, I will get to that. There's no time for me to discuss it today. But it's kind of hidden. So you can, what it does is it has a library of functions, okay? For you to, once you create, it has the make function, build, BDDs. After that, you can apply things. Sometimes it is useful to rename the variables in the BDDs because variable names are very much hardwired into the BDDs, as you know, because what you have is a function. A BDD may not have a particular variable name, but still be a function on the variable. It could be a function that actually uses the variable. So that is something that you should be aware of. So if you have a variable x and a variable x prime, those two, you may be using it, and there may be, two functions denoting the same thing as far as x and x prime are concerned, but they may not be the same thing. Okay. So in any case, so it has a whole bunch of functions that you will need, for example, existential, quantification, elimination, and so on. So you can already familiarize yourself with how to construct BDDs, how to kind of initialize your thing and so on. So, I mean, there is a manual that will be, we'll upload them as well. So we'll go through that on next Tuesday. Yes, it is CUDD if indeed you want to.
Yeah, thanks. I found it.
On your own, and I actually have. Just hang on. I thought I had it here. No, I have it here. So these are the three things that you. Yeah, there is a brief document in here which gives the overview, and then it's CUDD. Okay, I'm sorry, CUDD. These are some detailed documents. All this will be uploaded. We will upload it, and if you find any other documents, that you're free to. Okay. Any other questions? Okay.